Welcome to today's tutorial. Today we want to look at second order differential equations. Second order differential equations. We have been looking at first order differential equations from previous tutorials. So kindly, if you have not checked out them, kindly check them up there. Feel free to comment and leave a question that you feel you need guidance. I'll be able to respond to you shortly. Okay, before we proceed, remember to subscribe so that in time we post a new tutorial, you are the first one to get it. Okay, so today we are looking at second order differential equations. General second order differential equations is of this form. Okay, so if you look at this equation, you'll find that it's linear. It's linear. Every part, if you look at it, it's a linear equation. It's a linear equation. So it's of that kind of equation. So what you need to do here, we need to divide by the last coefficients. So in this case, our last differential or derivative is second derivative, and this coefficient is a2. So we divide every part by a2. Every part we divide by a2, including the solution gx. We also divide by a2. So that now we can write this general equation generally like this, like that. So you can see the a1 over a2 is our px, and 0 over a2 is our qx, and our capital gx over a2 is small g, function of g function of x, gx. So the solution of this kind of differential equations depends on px, qx, and gx. Okay, so in case you find that the qx, which is a coefficient of y, if it is equal to 0, you'll find that the dE reduces to that. And in this case here, we can transform these particular linear differential equations to a first order differential equation. Remember, first order differential equation is whereby the power or the derivative is actually 1. So in this case here, this is a second order derivative differential equations, because the highest derivative is y2, that is second derivative. So to transform it, we introduce this substitution way of doing it here, whereby we let z to be dy over dx. We let our z to be dy over dx. Now that means if we differentiate dz in with respect to x, then we'll get the second derivative of y in respect to x. So that means if we now go back to our general equations here and we substitute respectively, we come up with this second equation. That means if you look at this equation, second equation keenly, you'll find that it is easy to solve it. So after solving it, what do? We substitute back our z to our respective derivative. so that we are able now to get y. Remember, the solution should contain y. So for example, let's take an example so that we simplify our notes. So we have this kind of equation here, which is a second order linear differential equation. Now we want to simplify, to solve it. So first thing, remember, it will be converting this one to first order differential equation. And by doing so, we let z to be equal to the derivative of y, of x, in respect to x, and therefore we get dz dx, and we substitute respectively. When you substitute respectively, you'll find this one is true. So if you look at this equation here, it is now solvable. It is now solvable because now we have a linear homogeneous equations, and we can solve it using the relevant solution. We looked at this on how to solve this kind of equations from our previous tutorial. So if you have not checked on that, kindly check on the previous tutorials up there. And if you have a question on anything, leave a comment and we'll be able to respond to you as soon as possible. So in this case, we get what we call integrating factor. That's what I'm calling high F, integrating factors of exactness. So here, to get integrating factor, which is ux, we use this kind of relationship, which is ux is equal to E integral of p x dx. So whichever you can see tan x here, it is our px. We cannot see that. So if you integrate tan x, you get ln of secant x. And because it's exponential, then this solution becomes true. Again, if you have a question on any point of this, kindly leave a comment. I'll be able to show you how it is happening. So after that, since we have our ux, we multiply by our integrating factor all through. That's the reason we have this kind of equation here. Then we use that relationship again from our previous tutorial, so you can check on them. For now, we solve a given d in d using integrating factors, and you'll see this is true. That is true. So that next, our z, which is equal to this, is equivalent to this, is equal to that, which implies that our dy dx is actually that one. It's actually that x cos x, c1 cos x. Which means if we integrate, we'll get the value of y. We'll get the value of y, which is actually this. And therefore, opening bracket, integrating and opening the brackets, you get this is true. You get that one is true. And therefore, our solution, which is y, is given by this. Is given by that. So, by that, you see we have solved a second order differential equation using that simple transformation method. And for more tutorials, kindly subscribe, share also with your friends so that they will be able to get these ideas. And if you have any question, leave a comment. So thank you and bye for today.